chapter 10. First thing we're going to take a look at is the chi-squared goodness of fit. And what we're going to see is we're going to be given something that they're expected. They're going to expect this is going to happen. This is how the data is going to be distributed. Okay, because maybe somebody told them that, or that's just what they think it is. And then what we're going to do is actually take some kind of survey or collect some data somehow to find out what actually happens in that sample, and we're going to compare the two. We're going to basically compare what we observe, which is kind of the sample, okay? So we're going to take what is observed, again, which is kind of that sample, based it on what they told me what was going to happen, which is expected. Okay? So if maybe for an example, in a class, I would expect 50% of the people to like chocolate ice cream. That's what I would expect. That's what I would say, okay? Okay, depending on the size of the class, that would mean a certain number of people, correct? So if I had a class, this would be a really big class, but if I had a class of 100 people, I would expect 50 of them to like chocolate ice cream, right? And then I would go and actually survey them. And maybe I found out 60 of them liked chocolate ice cream. I was a little off. And what we want to find out is, was I close enough? How good did what I find fit what I thought was going to happen? Right? Does that make sense? How good is it going to fit? And what we're going to use there is chi-squared. Because you would agree, observed and expected is going to vary. So we're going to go to a variance, which is chi-squared, right? So you may want to dig through your folders and find your chi-squared distribution. And before we go too far, what are some of the properties of chi-squared that you remember from that distribution? What were some of the things that made it different? Anybody remember? Can't go negative. Why is that? That's a good... You are, well, you're squaring it, right? So it's not going to go negative. Very good. Where a lot of our other ones can, the normal distribution, and the other one, they can go negative. And so what's another one? Very important. And it's okay. It's a tough one. It fills from the distribution fills from which way? It fills from the right, right? It fills in this way, and then it keeps going, right? So that's one thing to remember. But also one thing we need to know is that degrees of freedom was important once we got to that as well, right? And a lot of times we did a chi-squared right and a chi-squared left and all that stuff. And we're going to discuss which of those are going to be important for us today. Okay? But first thing, we got to make sure that we can actually figure out, what do we mean by observed and expected? Because those are some new words, kind of, right? And so here there was an executive took a sample of 500 listeners because they were apparently told that classical, country, gospel, oldies, pop, and rock would have this particular distribution. So basically, no matter how many people I surveyed, 4% of them are going to like classical. That's what somebody told this broadcast executive, right? And maybe somebody told them 36% of those people are going to like country music, so forth and so on, right? But then they actually took a survey over there of 500 people, right, on the right-hand side. And they found out of those 500, 8 liked classical, 210 liked country, 72 liked gospel, so forth and so on. So of these two, which one would you call expected? Which one shows me expected data? The one on the left or the one on the right? Which one? You give me both answers. That's not fair. You can't say right and... Yeah, this is the expected. This is what I will expect to happen. Basically, this is showing me no matter what the sample size is, right? I should expect that percentage. Over here, then, is what I actually observed. This is actually what happened. So now they're speaking different languages, though, right? That's kind of a problem. And the language you're going to want to speak is the actual counts themselves, right? So over there, it was 8 people liked classical. Is that the actual count of how many liked classical? Right. But over here, it's 4%. Is that the actual count? No. Well, what we would do then is it's 4%, but of what? Well, in this case, it'd be 4% of 500, right? So you would take 0.04 times 500, and a lot of times what I do is I put it in parentheses, and I say I would have expected 20. Well, now right off the bat, I don't know about that, right? We've got 20 versus 8. So far, how's our survey looking? Yeah, not so good, right? Then the next one would be 180. 180, 210, well, that's not so bad, because that's a big number, right? That's hanging in there. The next one would be 55. Is everybody clear how we're getting these numbers? I'm taking the decimal times 500, right? And then 10. And then 90. And this is a little bit harder down here to do, like if you were doing them in your head. 145. So based on our expected versus observed, how do you think we're doing? Well, the first one's above, right? It's 20 versus 8. Well, or you could say the observed is below, if you want to talk, let's talk that way. The observed is below what we expected. The next one, what we observed, was actually above. And then above, ooh, equal, that's a good one. And below, and below. So we got a little mixture of both, right? So now, that's all you need to know for this point. Are we clear how to figure out which one was expected and which one was observed? Observed is going to come from some sample that was actually taken, where expected a lot of times, it's as if somebody told you that. Like, this is what's going to happen. Okay? So eventually we're going to test and see, well, how good was that, what they told me? So for example, what do you think? This expected over here, based on what we saw over there in our sample, do you believe this to be true? Do you believe it's good enough? This 4%, 36%, 11%, do you think that's good? Just a guesstimation. You're saying no? Okay. Well, we're going to find out. So the next thing we got to do before we actually finish this particular example, we're going to go back to that data. Okay. Before we finish that, here are the two conditions that we really need. The first one is the observed frequencies must be obtained using a random sample. Well, let's go back. Was it a random sample used? Based on what we see here in example 1. I think it was, wasn't it? It was what, the fourth word in, right? It says randomly, right? Selected 500. Okay, so we're good. Check mark there. And the next one says each expected frequency must be greater than or equal to 5. So each expected. What do you think about that? We're good. Why do you suppose they do that? Why do they make it like that? Any ideas? What are they trying to really control? Indirectly. They're actually trying to control sample size. If the sample is too small and you take 4% of it, you're not going to be above 5, are you? But if the sample's large, are you going to be good enough? Yeah, that's really what they're trying to control there, right? Because it depends on what percentages you have. The question was, why don't they just control n? That's a great question. But then it depends on what your percentages are, right? If we got a 22% and a 30%, you know, so that's why they try and control what number should be in there. Okay, good question. So we got both of those, right? So now that we know that, so it says right here, if it's met, then we're going to use, now here's something different, might want to highlight this. Our degrees of freedom is going to be k minus 1. What is it normally? What it has been? It's been either n minus 1 or n minus 2, depending on the situation, right? And what was n again? N was your sample size. Here it's saying k minus 1 is your degrees of freedom, where k is the number of categories. What do they mean by categories? Like in this last example, could you think of how many categories we have? We have 6 categories, right? We have classical, country. Now, it's not always going to be that, right? But we have 6, so we're going to take those number of categories. Not 500, but we're going to take the 6 in this case, right? So it'll be 6 minus. So our degrees of freedom here is going to be 5. You don't necessarily have to write that down yet, because we'll come back to that in a little bit. I just like to give an actual example. Then the test statistic for chi-squared, nice small formula, right? Okay, compared to some of them we've had lately. So chi-squared, what we're going to do is basically do this part for each category. And then once we do that for each category, what's that telling me to do? Add them up, right? Sum it. So it says observed minus expected. So let's think about that for a second. So if I take observed minus expected, that's pretty much going to tell me how far the two were apart from each other, correct? The difference between the two. Right? Isn't that what it's going to tell me? But then I'm going to square it. Okay, the reason we're squaring that, because again, if you start summing things like that, you got possibility of it being 0, right? And so we square it. And so that is also leading us towards the chi-squared. That's why we're using it, because we are squaring that. So all those numbers are going to be positive. Agreed? And then we're basically going to divide by, I kind of look at it as where did it start, the expected. It's almost like a percentage we're finding here, right? So it's close, but the squaring does throw that off a little bit. Okay. Any questions on the formula there? No? Well, that just kind of tells you that. Okay. Now let's think about this here. If these two values are really close to each other, the observed and expected, they're all really close. So when I do O minus E, is that going to be a big number or a small number? If they're really close to each other. Pretty small number, right? Then I'm going to square it. If I have a really small number and I square it, it actually gets below 1, it would actually get smaller, right? And then if they're really good, I'm now going to divide by something, e, so I'm going to make it even smaller. So if they're very close to each other, like really, really close, a lot of these are, each of these is going to be really close to 0, right? So when I add them up, it's not going to be a very big number, is it? But do I want them to be close? Yes, because that's what I want. But here's the problem. Our distribution looks like this, correct? You with me so far? So what if these two are really far away from each other? That's going to be a bigger number, correct? And then I'm going to square it, and that's going to make it even bigger. And then I'm going to divide that. I'll bring it back down a little bit, but it's still going to be pretty big, correct? Where do big numbers happen on this chi-squared graph? Do they happen on the left part of the chi-squared graph or on the right side? Where do big numbers happen? Well, you can't go negative, so big numbers happen over here, correct? So what we're going to say is basically our rejection region should always be over there, because big numbers are bad in this case, right? So for a chi-squared goodness of fit test, what type tail test are you always going to do? You're always going to do a right-tailed test. Okay, you need to write that down somewhere. It might actually be written a little bit later. But that's really important. Can you see why? Because I want it to be really close. So I want to be able to support the fact that they're really close together, right? So I'm going to put that in the alternate. So in the null, we're going to put, that it's bad, right? And so then we can reject it. So that's why it'd always be a right-tailed test. Okay? You be okay with that? Again, I could have just said, oh, it's always a right-tailed test, but then it wouldn't have made any sense. You'd be like, okay. Okay, but that's the reason. If they're not very close, it's going to be a big number. If they're close, it's going to be tiny, right? And I think that's actually what it says right there. So we only really want to reject it when they're not close, which is why we throw it as a right-tailed test. So we already know that they claimed earlier that the distribution should be that, correct, over there on the left? That's what they're claiming. And they found out that it was these other numbers. Oh, okay. So we randomly select 500, right? We have that. We're going to use alpha being 0.01 and example 1, and we're going to actually perform the goodness of fit test. So let's go. So the null is that, and I'm going to paraphrase this. If you are going on and going to be taking the AP, you should write it out all by hand. Okay, but I'm going to very much paraphrase. I'm going to say the percentages actually are, what is it, 4%, 36%, so right? Keep going. You should really write it much more official if you're taking it, because that's what they're claiming, right? That's actually what it is. Okay? So then what's the alternate? They're not. The percentages are not 4%, 36%, blah, blah, blah. Now do you possibly see why I took the time to focus on why it's always a right-tailed test? Because if we look at the alternate right now, which is normally where we look for what tails, correct? This would tell you a two-tailed, right? But that's, for goodness of fit, it's right-tailed all the time. Okay? No messing around with this. So, but remember, it's only for this one. Don't go back to those other ones now and be, oh, it's a right-tailed test. Okay, it's only for this one. Okay? Well, now what's some important information? Well, we got to get the test statistic. But before we even get going on that, what's a lot of times things that we find? Well, that's what in this problem is degrees of freedom, right? And what did we find out early? It's 6 minus 1, right? So it's 5. The one thing I always find first, I'm not really sure why I find it first, but I always go and find, no matter if it's Z or T or what it is, I always go find that critical number. That one that highlights where the rejection region is for me. Okay? And so why don't you go ahead and find that right now. Look at your table. We got degrees of freedom of 5, right? And alpha is 0.01. Boy, that's not a very big alpha, is it? 0.01, ooh. It's not looking so good for this, for us here, right? So that's where he said it's right-tailed all the time. Let's find that cutoff number. Anybody think they found it? That's correct. 15.086 is correct. Well, now we got to actually go find the test statistic and compare it to 15.086. Okay? So let's actually go find chi-squared, which is observed minus expected squared over expected for each one, right? So if you flip back, which classical was expected was 20, right? And classical observed was 8. So again, it's observed minus expected, though. So for that one, it would be 8 minus 20 squared over 20. Everybody clear on that? That's for classical. Now we know we're going to have to add them, so we might as well put a plus sign in there anyways. See how I'm doing each category? I'm going, right? So the next one, so what is observed for the next one? 210, right? So it'd be what, 210 minus 180 squared over, ooh, that's 210s, right? It looks like almost like 240 or something like that. Over 180 plus, I'm going to run out of room. Is everybody clear where these numbers are coming from? Okay. Plus 72 minus 55 squared over 55 plus, I got this one. I like this one. All right, 10, and then I can't even write it. 10 minus 10 squared over 10. That's going to be a fun one to add in there, right? We like that one. Plus 75 minus 90 squared over 90 plus last one. And I normally keep these very, very small because not all of you have the goodness of fit test on your graphing calculators. You need the TI-84 or further to have it. The 83s do not have it, unfortunately. That's one of the things they realized they really should have had in there and didn't. So why don't we kind of work together and maybe find some of these decimals. What's that first one, like 7.2? Is that what the first one is? That's making me a little nervous already. Why am I getting a little nervous already? We've only done one and we're almost halfway to our 15. You know what I mean? And some of these aren't looking very good. I like the 0. That's going to help, but I don't know. This isn't sounding too good. Because what do we got for that second one? It's got to be 5, isn't it? Uh-oh, we're already at 12.2, and we've only done 2 of them. Plus, this one's also pretty big, isn't it? what was it, 5.25? Plus, I got this one, 0. I'm glad I could help. That one's not terrible. But we're already at 17. You know what I mean? What was that next to last one? Did I have that one written down? 2.5? Yeah, I was going to say, that one wasn't as bad, but we're already past it. So almost at this point, you're like, who cares, right? But the last one, ooh, that gets kind of, well, no, it's not that bad. What'd you get for the last one? 2.76. So if we add that thing all the way up, it's, what are we looking at there? 20 something. Yep. 2271? Yeah, we knew pretty early on this one that this wasn't looking so good. So we're here, right? In the rejection region. So really, what does that mean for this then? Yeah, we're in the rejection region. So the percentages that I was quoted by somebody, or the percentages I expected, I don't think are very good. I can reject that claim, right? Because that's where the claim was in that right here. Because someone had claimed that we were testing whether we thought that was good. That's why we took a sample, right? That's why we spent all that time. And let's face it, our chance of an oops on this one of 0.01 is pretty small. So we can say with a pretty good degree of confidence that those percentages are inaccurate, right? Now, keep in mind, I might have been in a certain area of the United States, which might change our data, right? If I go more global, it could change quite a bit. But based on what we've seen, we can say, yeah, that's not good. And you can see which one was the main contributor was actually that first one, right? It was the main contributor down there, and that was probably the one that seemed, you know, like it wasn't going to cause that big of a problem. So you would say something like at 1%, I have enough evidence to say that the distribution is not what was claimed, not whatever the statistician came up with. I don't know where they came up with it, but I'm not agreeing with it right now. Any questions? Okay. Because I'm actually going to leave the second one right here. It looks more intimidating, but I was a little mean. I put some information in there that perhaps you don't need, and it's your job to weed it out. Okay. This one is actually smaller than the one we just did. The number of categories is smaller. All right. So go ahead, and once again, the thing here is we are going, it says right here, if you get looking at it, it says to test the distribution. So once again, we're testing that what we expected to have happen. That's what's really being tested. So put that in the null, because I kind of want to be able to reject that, say, yeah, that's not good. Okay. Because again, we want to basically figure out that it'll be good if the observed and expected is very small. But we have to do a right-tailed test. You see what I'm saying? How that has to work that way? We have to do a right-tailed test, but we want O and E to be close, which is really on the left side of the graph, and so it causes problems. Okay. Any questions before I stop recording? Oh, irradiation. Basically, I'm sure you've heard of it, of radiation. Yeah, exactly. Yum, yum. Well, it's either that or a lot of times with the ground beef, I say there's a lot of E. coli possible. They actually bleach it in ammonia, and then you get to eat it. Yum, yum. Let's go to McDonald's right now. Oh, there is burgers for lunch, too. That's hilarious. Of course, not everybody listening to the recording are going to have burgers for lunch today, but that is what we actually have today.